All right, I'm gonna take one more video before going home. So this is the third video lecture in the third week. So now we are going into chapter 5. Okay, so in the previous video, we studied the inverse matrix and remembered by the third property of the inverse matrix, if such matrix exists and that matrix is uniquely determined, all right? So whenever we have a system of linear equations like this, and we can convert it into matrix form, and if the coefficient matrix has an inverse matrix, A inverse, then by pre-multiplying by A inverse, we have a unique solution to that system of linear equations. That is, A inverse, that is unique, and B, that is given, exogenously given. So we can compute the product, and we have a unique value. That's going to be solution to the system. All right. So in chapter 5, we are going to address two questions. When that matrix when that coefficient matrix has an inverse matrix. And the second question is, if that matrix exists, and how to compute that. Right? So we are going to study one by one. And in this video, we are going to address the first question. So when n by n matrix is invertible. And we are going to establish a very important theorem. So we are going to give two sufficient and necessary conditions under which matrix A is invertible. The first one is the rank of a matrix is equal to n. Okay. And the second condition is, this is a typo. This is typo. The determinant of A has a non-zero value. Okay. Under either of these two conditions, matrix A has a inverse matrix. So the system of linear equation with that matrix A being a coefficient matrix, we have a uniquely determined solution. Okay. So in this video, I'm gonna talk about the first condition, the rank of a matrix. Okay. In order to explain that rank, I need to digress a little bit. So this topic comes from section 4.3. So there is one more topic I didn't address in chapter 4. That is the relation between vectors and matrices. But I already highlighted there is a close relationship between these two because a matrix can be put as an array of vectors. So in fact, matrix algebra is a natural generalization of vector algebra. Okay. And the formal definition of a vector is a element of a vector space. So we need to define vector space, but this is beyond our class because we are going to study mathematical tools for economic models. But almost every economic model in undergraduate program is defined in Euclidean space. Okay. So I think it's enough to define vector in a Euclidean space. In Euclidean space, for example, n-dimensional space, vector is defined as ordered n tuple numbers. Okay. So in two-dimensional space, one vector has a two, so one pair of numbers, and this is ordered, so the order matters. And in three-dimensional space, we have three numbers, and so on. Okay. And this concept vector is from physics or mathematical physics. And so one vector is used to represent magnitude and direction. And those two components are well visible in two-dimensional space or three-dimensional space. So let me show you one diagram. So here we have a two-dimensional space. One vector, 3, 2, for example, indicates 1 point, right? And if we draw a ray from the origin, and the length of this ray characterizes the magnitude of a vector. So the magnitude of a vector is given by the distance from the origin. So using the distance function, so in case of a two-dimensional space, we don't have this distance function because we have a Pythagorean theorem. So because this is a right triangle, we can easily compute the length of this arrow using that theorem. That's going to be a square root of 13, I guess. Square root of 3 squared plus 2 squared, right? But this definition can be extended to n-dimensional space. So the distance function from the origin to a one vector v, that defines the magnitude. So magnitude is denoted by these double bars, okay? So double bars of v is a magnitude of vector v. So that is square root of the summation of each component squared, okay? So using the dot product, we can rewrite this square root of v dot v, okay? The dot product of itself, because vector v is v sub 1 to v sub m, and v dot v is a summation of these component squared. You can easily check that, right? And in general, distance function measures the distance between two vectors, u and v. So that can be computed by this, okay? So we first compute the difference for each component, and then take square, and then add all them together, and in the end, we take the square root, okay? Let me show you just one example, because that is not that important. So we have vector u, say 1, 0, 1, and vector v, say 3, negative 1, 2. Then the distance between these two is going to be square root of 1 minus 3 squared plus 0 minus and negative 1 squared and 1 minus 2 squared. So it's going to be 4 plus 1 plus 1, I guess. So square root of 6. Okay. So even in even any two vectors in n-dimensional space, we can compute the distance using this formula. Okay. And regarding this formula, there is one more fact, which is called a triangular inequality. And let me introduce that right now. So the idea of a triangular inequality, which is presumably one of the most basic inequalities in mathematics. So if you study math further for analysis such as a real analysis or topology, you're going to make use of this inequality several times because that is a basic inequality. So the basic idea of this inequality comes from triangle. If you have one triangle, then we know the sum of the lengths of any two sides is larger than the length of the other, right? So if this is x and this is y and this is z, then x plus y is always larger than z, right? And using this idea, we can define triangular inequality. Suppose, we have a two-dimensional space, and then, each vertex of this triangle defines one vector, right? So let me call this vector u, and this is vector v, and this is vector w, okay? And each can be seen as a one vector, right? And then the length of the side z is nothing but distance between two vectors, u and w. That is z, okay? And x can be expressed as distance between w and v, and y, distance between v and u, okay? So x plus this is x, this is y. So x plus y should be larger than z, so we have this triangle, or this inequality, okay? So given any three vectors, we can set the upper bound for a one distance. That is the primary role of this inequality. And once again, it's used over and over. in a advanced math class. And let me just say introduce that inequality. I think in our class that is not that important. All right. So geometric interpretation. So I think you've ever seen this before. For addition, the sum of the two vectors becomes a diagonal formed by a diagonal of the parallelogram formed by these two vectors. So we have 1, 4 and 3, 2. Then the addition becomes a 4, 6. Right? So we just add each component to find the sum of two vectors. All right? So the geometric interpretation is we first move from the origin as much as vector v, and then we have to move the northeast as much as vector u. So moving this point by 3 units to the east and 2 units to the north, then we can reach this 4, 6, and that is a diagonal of this parallelogram. And the negative scalar multiplication indicates the opposite vector. So suppose we have a vector 3, 2 that is right here. Okay, let me call this vector u, and the negative u is gonna be the opposite direction. So it changes the direction of the vector diametrically, like this. Okay. Then once we define negative multiplication, scalar multiplication, then we can define the difference between two vectors, right? Because a v minus u is an addition of this v, the sum of this v and negative u. Okay. Once again, it has so the geometric interpretation is that is a diagonal of a parallelogram formed by these two vectors. Okay. And for the dot product, so we already studied how to compute the dot product. This also has a geometric interpretation in two-dimensional space or in three-dimensional spaces. So suppose v and u are two vectors in these spaces, then the sign of the dot product indicates whether the angle between two vectors is acute, so smaller than 90 degrees, or obtuse, so larger than 90 degrees, or right, so equal to 90 degrees. Okay. So if the dot product has a positive value like this, the dot product between these two has certainly a positive value. That means the angle between these two vectors, this angle, is smaller than 90 degrees. Okay? And if the dot product has a negative value like this, then the angle between these two, formed by these two vectors, is obtuse, so larger than 90 degrees. And one interesting thing is when dot product has a zero value, like think about these two vectors, 0, 2 and 0, 1, 1, 0, 1, 0 and 0, 2. Okay, its dot product is equal to 0. Okay, so whenever two vectors have zero dot product, then its geometric interpretation is two vectors are perpendicular to each other. Okay, and this might be important. Okay? This might be important when we study optimization theory later. Okay, so I digressed a little bit about vector algebra, and now we are going to study the rank or the rank of the matrix. Okay, so in order to define rank of a matrix, we have to start with this linear combination. And linear combination of two variables, x and y, takes this form, a sub 1x plus a sub 2x. So minus x plus 2y or 3x plus 6y are examples of linear combination of two variables x and y. Okay? And this expression is extended to n variables. So suppose we have n variables from x sub 1 to x sub n, and the linear combination takes this form. Okay, So summation of a sub a times x from so where the subscript from so where the subscript k goes from 1 to n. Okay, so we've seen this expression before. That is a dot product, right? So if we define vector a as a sub 1 to a sub n, and vector x as x sub 1 to x sub n, the linear combination is nothing but the dot product of a and x. Okay? But somehow this concept, this expression, linear combination, can be extended to n vectors. Okay? So now we just change the variable to vector. So change that x1 to v sub 1. So here v sub 1 is a vector. Okay? So we can think of linear combination of n vectors. Okay? So that's a linear combination. And this concept, this expression, leads us to the next important topic. So important concept in linear algebra, that is a linear independence. This is important. All right? So let me first read the definition. So suppose we have the set of n vectors. Okay? So from v sub 1 to v sub n. Each element is a vector. Okay? And if any one of these vectors can be expressed as a linear combination of the others, then we say the set of these vectors is linearly dependent. Linearly dependent. Okay? So suppose that v sub 1, the first element, can be expressed as the linear combination of the others. Say v sub 1 is a sub 2 x2, v2, plus a sub 3 v3, plus a sub n v sub n. All right? Then I can move this v sub 1 to the right-hand side. Okay? So to make the left-hand side be equal to 0, then minus v sub 1 plus a sub 2 v sub 2 all the way to a sub n v sub n. All right? So this means, oh, by the way, if we define a linear combination of n variables or two variables or n vectors, these scalars, a sub 1 or a sub 2, a sub n, these vectors are non-zero vector, meaning that some scalars may be zero, but not everyone. Okay? Because if every scalar is equal to 0, then the linear combination boils down to 0. It has a no meaning, right? So at least some scalars should be a non-zero numbers. Okay. So here, another way to define linear dependence is there exists scalars from a sub 1 to a sub n, not all zeros, such that linear combination of these vectors is equal to 0. Okay, here is a one example. If v sub 1 can be expressed as a linear combination of the others, then we have a linear combination of n vectors such that its linear combination boils down to 0 vector. Okay, because we have a non-negative, so we have a non-zero scalars, because we can make sure the a sub 1, that is negative 1, so non-zero number, and one of these numbers, scalars, is a non-zero number, so we have a linear combination on the right-hand side. Okay? So then we say the vectors are linearly dependent. On the other hand, if there exists no such scalars, meaning that the only way to make this equation, the only way to make this equation hold is all scalars are equal to 0. If a sub 1 to a sub n are all 0, then clearly this equation holds, but that is not a linear combination. Okay? So there is no such linear combination having 0 value. Then we say the set of vectors are linearly independent. Okay? So this might be a little bit tricky, but if we do some examples, I think this concept will be very clear. So here, let me do the first exercise, okay? So in exercise A, we have two vectors, 1 and 1 and negative 3, 2, okay? So in order to check whether these two vectors are linearly dependent or independent, okay, we have to set up this equation. So we have to examine whether there exist two scalars, a sub 1 and a sub 2. So the linear combination of these two vectors is equal to 0. Okay? If there is a way to make this equation hold, then these two vectors are linearly dependent. Okay? Then think about this equation. Distributing a1 and a2, we have a1 minus 3a2 as the first coordinate, and the second coordinate becomes a sub 1 plus 2a sub 2. Okay? And this is a zero vector defined in two-dimensional space because these two vectors are two-dimensional, defined in two-dimensional space. So we have two zeros on the right-hand side. All right. So now we come up with a two linear equations, system of linear equations, a sub 1, this is 0, and a sub 1 plus 2a sub 2 equal to 0. Okay? And if we think about the solution to this system of linear equations, and you're gonna easily catch that, so you can easily see that, the only way to the only solution to this system is both a sub 1 and a sub 2 are equal to 0. Okay, there are no other scalars, a sub 1 and a sub 2, can make this linear combination be equal to 0 vector. All right. So by definition of linear independence, now we can see these two vectors are linearly independent. All right. So in two-dimensional space, it's very easy to see that whether two vectors are linearly independent or dependent, because if these two vectors were linearly dependent, then there are two scalars, non-zero scalars, right? So 1, 1 becomes a negative a sub 2 over a sub 1, negative 3, 2, meaning that one vector can be expressed as a scalar multiple of the other vector. All right? So in case of a two-dimensional space, in this way, we can easily tell whether two vectors are dependent or independent. Okay? Think about the second example, 1, 0 and 1, 1. Is there any way to make the one vector as a scalar multiple of the other? No, because we have a 0 here and we have 1 here, right? So we can easily see that one vector is not a scalar multiple of the other. So these two are linearly independent. Okay? In three-dimensional space, okay, now we have to think about whether one vector can be expressed as a linear combination of the other two, right? Think about the exercise D. Okay, there is no way. All right, but if the second coordinate in the first vector was a 2, then these three vectors are linearly dependent because a first vector with this a revised number 2 Now the first vector is the sum of the other two vectors. Okay, so there is a one way to express that one vector as a linear combination of the other two, because this is just the sum of the other two vectors. So now these three vectors become linearly dependent. All right. All right, and this concept, linear independence, can be applied to matrices because a matrix is an array of several vectors. So, in that example, 5.2, are the rows or columns linearly independent in each of the following matrices? Think about the first matrix, 2 by 2. We have two row vectors or two column vectors, and every vector is a two-dimensional vector, right? And there's a no way to make the so there's a no way to make so there is a no way to express the first row vector as a scalar multiple of the second row vector, right? So they are linearly independent. And in the second example, we have 2 by 3 matrix, and so two row vectors defined in three-dimensional space, right? So in order to make a scalar multiple, so in order to express the first row vector as a scalar multiple of the second, we need to multiply second row vector by -2, right? Then the first component becomes 2, and the second component becomes -4, but unfortunately the third component becomes -2, right? So they are different, meaning that the first row vector is not scalar multiple of the second row vector, and vice versa. So we have two linearly independent rows in the second. Okay, let me leave the final matrix for exercise. Now we are ready to define the rank of a matrix. Okay, suppose A is n by n matrix. Okay, and the rank of that matrix is defined as the number of linearly independent rows. Okay, so here, because we have two linearly independent rows, the rank of this matrix is 2. Okay, and similarly, we have two linearly independent rows in this matrix, so the rank of this 2 by 3 matrix is 2. Okay, and one thing you have to notice is the rank. So the number of linearly independent rows cannot exceed minimum number of m and n. So the number of rows and number of columns. Think about this example. Okay, we have two rows, so the rank of this matrix cannot exceed 2. That is quite straightforward. But think about the columns. We have 3 columns, but these 3 columns defined in two-dimensional space. Can you have 3 linearly independent vectors in two-dimensional space? No. You know what? In n-dimensional space, the number of linearly independent vectors is n most n. All right? So this is why in two-dimensional space, we need a two-axis, okay? With two linearly independent vectors, unit vectors, 1, 0, and 0, 1, we can express every vector defined in two-dimensional space. Say A, B is a linear combination of these two vectors. A times 1, 0 plus B times 1, 0, or 0, 1, right? So with these two unit vectors, we can express every vector defined in two-dimensional space as a linear combination of these two. All right. So there are only, at most, two linearly independent vectors in two-dimensional space. Likewise, we need three axes to describe a three-dimensional space, right? So 1, 1, 0, 0, and 0, 1, 1, or 0, 1, 0, and 0, 0, 1. Okay? With these three unit vectors, we can characterize every vector in three-dimensional space as a linear combination of these three vectors. right? So in three-dimensional space, there are at most three linearly independent vectors. Okay, so going back to matrix, if we have an m by n matrix, the rank, the number of linear independent rows, cannot exceed a minimum number of m and n. Okay, so if the rank r is equal to minimum number of the number of rows and number of columns, then we say matrix A has full rank. Okay, so this is an example of full rank matrix because a number of rows and number of columns are equal to 2, and the rank of this matrix, the number of a linear independent rows, it turns out to be 2. So this matrix has a full rank. Okay, this matrix also has full rank. All right. Otherwise, meaning that if R, the rank of a matrix, is strictly lower than minimum of m and n, then we say the matrix is a singular. All right. Okay. So in case of a 2 by 2 or 2 by 3 or 3 by 3, if a matrix has a low dimension, it's not that difficult to determine the rank of that matrix. But for a matrix of a large dimension, it's often difficult to compute its rank. So here is one way more efficient way to determine the rank. It is called the Echelon Transformation. Okay? So the idea of this transformation is we transform the given matrix A into an echelon form by means of these three operations. First, we can switch any rows within the matrix. And second, we can multiply by scalar. We can multiply a row by scalar, right? Or we can divide by non-zero scalar, right? And the third operation is any row can be replaced by so the any row can be replaced by the addition to scalar multiple of the other row vector. Okay, so using these operations, we are gonna make use mostly the third one, row addition. Okay, so any row can be replaced by so the addition to scalar multiple another row vector. Okay, to transform the given matrix into echelon form. By the way, echelon form means so one matrix is in row echelon form if each row has more leading zeros than its predecessor. Okay, so the first row is a leading entry is 1, and the second entry is 2. All right, and then on the other hand, the second row vector 0, 3, it has a 1 on 0 in the front, right? So that it has a 1 leading 0. Okay, so that is an echelon form. This is also in echelon form, okay, because the second row has a 1 leading 0. This is another example of a echelon form. Second row has a 1 leading 0, and the third row vector has all 0 entries. Okay, so each row has a more leading zeros than the predecessor. Then we say matrix A is in a row echelon form. All right. So now let me illustrate how to transform the given matrix into an echelon form using these three operations. Okay, this is not that difficult. So here we are given 2 by 2 matrix A. All right. And in order to transform into echelon form, we have to make this leading entry in the second row be 0, right? So the way to make a 0, so in order to have a 0 entry as the first entry, so now we multiply negative 2. Okay, we multiply the first row by negative 2 in order to make negative 2, okay? And then add this to the second row, right? then we are going to have 1, 3, and then 0, minus 5, negative 5. Because 3 times negative 2, that is minus 6. So 1 minus 6 gives us negative 5. All right. Now we have 0 in the second row. So we have 1 leading 0 in the second row. So that is an echelon form. Okay. Similarly, we can transform matrix B into echelon form. So first, we have a leading 0 in the first row. Okay. So we first interchange first and second. Okay. So 2, 6, 2, 0, negative 11, negative 4, and 4, 1, 0. Okay. And first, we have to transform this number 4 to 0. Okay. How can I do that? We need to multiply negative 2. So we need to multiply the first row by negative 2. Okay. And we have negative 4. And then add it to the third row. Then we can transform this 2, 6, 2, 0, negative 11, negative 4. And that addition gives us 0 and negative 11 and negative 4, right? And then the third row has to have more leading 0 than the second row, okay? But the second row and the third row is the same, right? So we just multiply the second row by negative 1 and add it to the third row, and we can transform one more time. 2, 6, 2, 0, negative 11, negative 4, and 0, 0, 0. Okay, so it turns out that so this is now in echelon form, right? Because the third row has 3 leading zeros, second 1 leading 0, and the first one is a no leading 0. Okay, so each row has a more leading 0 than the predecessor. So now it's an echelon form. And one thing you can notice is matrix has different row echelon forms, even the first one. Okay, we transform this matrix to this echelon form, but we may start with row switching. So first transform to say 2, 1, 1, 3. Okay, now how to eliminate this number 1? We multiply negative 1/2. So we multiply the first row by negative 1/2, then we can make negative 1 and add it to the second row. Then we have a 2, 1, and 0, 2.5, right? This is also echelon form. So one matrix has many different echelon forms depending on which operation you use first, right? And this is very analogous to the elimination method for solving linear equation system. Think about this equation. Say x plus y is 3, and 2x minus y is 0. And by way of elimination, say if we want to eliminate x, we multiply negative 2. So we multiply the first equation by negative 2, right? And add it to the second equation. Then we can eliminate this x so that we can find the value of y. And then we can substitute the value for y in order to find the value of x. So the solution to this linear equation system, right? So this echelon form transformation is very similar to that elimination method. Okay. Now the important thing is how to determine the rank of a matrix. The rank of a matrix is determined by number of non-zero rows. Okay. So in matrix A, echelon form has a 2 non-zero rows. Okay, 1, 3 are non-zero vector, 0, negative 5 non-zero vector. Okay, So the rank of matrix A is 2. Okay, what about matrix B? After transformation, we have a 1, 0 vector in the last row, but the first two rows are non-zero vectors. Okay, so although this is a 3 by 3 matrix, so the number of linearly independent rows may be 3. Okay, it turns out that matrix B, the rank of a matrix B is just 2. Okay, so matrix A is a full rank matrix. It has a full rank 2 by 2 matrix, and we have 2 non-zero vectors in echelon form, meaning that the rank of a matrix is 2, the same as a dimension of the matrix. So the matrix A has a full rank. On the other hand, the matrix B is a 3 by 3 matrix. Okay, so the dimension of a matrix is 3 by 3, but the number of the rank of a matrix turns out to be 2, smaller than that dimension. Okay, so this matrix B is a singular. Okay. All right, so let me do just one more exercise about this transformation. So use the method of Echelon Transformation to compute the rank of each matrix. All right? Look at the first matrix. This is already in echelon form, right? And then we can easily tell the rank of this matrix. It has 2 non-zero row vectors, so the rank of this matrix is 2. All right? And then think about the second matrix. All right, so I first need a 0 entry in the second row, and the way to eliminate this, okay, we just subtract. So we just subtract the first from the second. Then we have 3, 1. Okay, and the second vector after so if we find the difference, then we have 0 and 3 and 1 and 1 and 1, right? I just take away the first row vector from the second. Let me make sure, just double check whether this is correct. All right. And 1, 3, negative 8, 4, and 5. And similarly, we need 1, 0 in the third row. So we take away the first row vector from the third one. So 1, 6, and 0, 3, 1, 1, 1, and 0, negative 3, negative 1, and 1, 1. Okay, and we need more leading zeros in the third row. Okay, and the way to do that is we just add the second row to the third one. Okay, then this becomes a 0, this becomes 0, and this becomes 2, and this is 2. All right, now it is an echelon form, and we have 3 non-zero vectors, so the rank of this matrix is 2. Okay, and let me leave the final matrix for exercise. Okay, so in this video, we studied how to determine the rank using the Echelon transformation, and the rank plays a very important role in the future. So when we decide, when we determine whether system of linear equation is solvable using the inverse matrix or not. Okay, so that is very important. So I highly encourage you to do many exercises for this one. All right. So this is the end of the third video. And after going back home, let me think about whether taking another video or not. All right. And if I do not, then let me upload the last video tomorrow morning. All right. Hope you guys enjoyed this video, and see you in the next.